will plan on stopping around noon because I don't want food to get cold. So. Not because I'm hungry.
Okay. Now, what is the problem with the back of words? One of the problems, it does not allow us to generalize well. And ideally we would like to be able to pre-train stuff on a labeled data or go from one domain to another. Like here, it is a pretty famous example for tagging the images with the text. So there is a convolutional neural network that does image recognition. There is a recurrent neural network for generating text description, and they learn the transformation between these representations. And it is really cool, among other things, because it can predict the representation of the things that one of the sides never has seen. And here we have a word for cat, but the network never saw images of cats. Right? And then when we feed to it for inference an image of cat, it lands near this word cat. So we'd like to do something like this, but how to do it? And since I learned about all these concepts from working on recommendations, and that's what I'm going to use here to illustrate it. So we have items. We would like to recommend some items based on user profile, or maybe based on what someone is seeing now. Like we have movie recommendations, for example, and the user has just clicked on Pulp Fiction. And what can it mean? By the way, Pulp Fiction doesn't say much about the user, but still. So it would be nice to come up with some similarity score, which could be the probability that the user would be interested in item 2 given item 1. Or the probability that a given user knowing everything about it from their profile would like some item. So collaborative filtering was really popular starting with this Netflix prize. Everyone was talking about SVD and SVD++ and whatnot. So this is a really simplistic explanation of what it does. Let's say we have a number of users and a number of movies. And we are asking ourselves whether a given user would like a given movie. And even without any calculations, it looks like he would like it because, user Sashko is similar to this user Mateos. They have one movie in common. And probably he would like it. And he's also similar to user Tomek by one movie as well. So maybe this is a good recommendation, but we cannot yet come up with a numerical score for it. And so there are a few ways to manipulate these vectors if we represent the user as a vector of the movies that he watched. Or we can represent a movie by the user IDs that interact. Then we can do, take dot product or take the cosine distance. So this third step is called limited unit product. And know to what extent things are similar. But still, this does not allow us to generalize too well, because we could have users that never watched the same movies, but they were watching movies similar to what the third user watched. So this kind of chains of inference are still not available here. One more thing with counts. The problem with counts is that if we have a matrix of it, and we would like to approximate it somehow, then the most popular things will dominate, and therefore they use, instead of concurrences, they use different flavors of pointwise mutual information. So this is the log from the probability that the items would occur divided by the probabilities that each individual item will occur. So PMI is one of these things that likes go into minus infinity, so if things never occur. And this could be a problem because if we have a sparse matrix, most of the things don't occur. And this matrix of PMIs is often replaced by the matrix of positive PMIs. which means that we exclude those values that are below 0 or equal 0, maybe even. And then we still have a sparse matrix, and then we try doing something with it. And the thing that we try doing is to factorize this matrix the way that the result of some operation between these short vectors that represent the user and the movie will be similar to what is on the intersection. And even more so, if we make this matrix factorization and we like multiply stuff, if a user never interacted with a given movie. And this is actually what is interesting in recommendations. It's not something fancy to recommend you something that you already watched. But if we are able to generalize, if we are able that, hey, this number is probably like close to 1 or something, then it would be a really great thing to do. And so therefore, all these SVD-ish things that originated from Netflix Price and others, which tried to estimate, something related with the probability that the given item appeared in the user profile. Which, if we have some separate talk sometime about personalization, this is not like the best goal to optimize for, but this will be the goal. And so these short vectors that we come up with when factorizing the matrices are called embeddings, because we are kind of embedding the larger and more complex space into something lower dimensional and simpler. And there we can measure the distances just like we tried measuring the distances between these vectors of co-occurrences. And we have a user Sashko, he will be close to some movies, he will be further away from some movies, and we could again measure either Euclidean distance, which they rarely do, but more often like cosine distance or dot product. So there are subtle differences between these distances, but what matters now is that there is some metric to tell if two items are similar or not. So they use pretty much the same in natural language processing. And it tells you, you know that there is this distributional hypothesis in statistics, like you should know a word by the company it keeps or something like that. So linguists say, oh, we knew it like forever, right? That words are really determined by the context. So these embeddings in NLP seem to capture semantics almost too well. And we will see the illustration in the next slide, unless you're already familiar with it. But if we determine the meaning of the word, if we represent the meaning of the word as some approximation of the context, then the antonyms would appear often in the same context. Like we had an awesome lunch in this restaurant, we had an awful lunch in this restaurant. And there is a high chance that these vectors for these words will be close, which is a problem with using embeddings without further training for things like sentiment analysis. And also there is this phenomenon of polyphony, and this is why I prefer analyzing user profiles to analyzing text. Because in the user profile item with ID this and this means only one thing. While here there is the Bank of the River, and there is the bank as financial institution, there is an Apple as a fruit or recording studio or company. And embeddings capture these many meanings in a pretty elegant way. It's just, the centroid of the things, but it's a centroid weighted by the frequency of occurrences, kind of, or by the power with which it interacts with other words. And then if you pre-train embeddings on the corpus from banking, then your word for bank will be very far from river. So, talking about capturing the semantics and why too well, after word2vec, there were this, things that we can really do arithmetics on these vectors that represent words, and that, like, man, if we take, let's start, like, king to the queen is the same, like, distance and similar vector to man to woman. But in reality, when it works, when you see demos of it, there are some simplifications made, because we can end up as a result vector of king minus 1 plus woman, still very close to king, and then they say, oh, since this is what we started with, we will exclude it, and then magically it is queen, so it's not always true, but it's pretty elegant, so it certainly knows something about language, this embedding thing. So there was this paper in 2013, distributed representation of words and phrases by Thomas Mikov and others. So they tried building these embeddings not by explicit matrix factorization, but by trying to predict the words in the context or the other way around. So there are a few approaches. But there were a few things that were really novel to it. And among those was cutting this head of the Ziphian distribution, so they have a threshold on the probability with which a given word appears. Then they manipulated the context window, and the results were that if we increase the size of the context, then we capture more of semantic stuff, and if we decrease the size of the context window, then there is more like syntactic relations. And one of the elegant things that they used was negative sampling. This is the copy-paste from the code by Nico. So negative sampling, as opposed to softmax or anything like it, allows you to work with the classifier for many classes. Like if you have, I don't know, 20,000 words in your vocabulary, or if you have like millions or billions of YouTube videos, it starts hurting at some point. And although there are these performance optimizations like hierarchical softmax and whatnot, negative sampling is still the preferred one. So negative sampling works like this. We take one positive example, and then for one positive example we have like n negative examples, and we want obviously to maximize the value for positive, to minimize the value for negative. And this number of negative examples per one positive is one of the hyperparameters that you have to adjust. And if we say that all these, word2vec techniques approximate the matrix of positive PMIs, this negative sampling hyperparameter influences the shift of it, so this will be shifted positively. But this is more of a technical detail. In general, it all works the same, but this is just one of the novel things. So in word2vec there were two approaches to what we are predicting. There was continuous back of words and skipgram. And though essentially they're kind of the same, this skipgram is predicting context from the word, not the usual task of predicting word from the context. And there are arguments that it allowed to generalize better because we have smoothed out the stuff or something, but you really have to see it. It depends upon what you want to achieve.
Sash?
Yes?
Can you spend a couple more minutes on word2vec, because I think many of us here don't really know, and I think it's important to go over.
Wait a minute. Okay, so what word2vec does? We have a piece of text, some window, for example, I hate soup. Let's say that we are now on this word soup, right? And there is a vector representation for each of these words. So this is a series of numbers. So in reality, there are two vectors in word to vector for each, but let's simplify. And we want to take the context vectors as inputs, and then try to predict the word soup from them. So again, we may express it with, there is coefficient for like each of these. So this thing we add, there is a coefficient P1, P2, P3, and we try to adjust those so that, you know, our classifier predicts the IT for soup. This could be even predicted the vector, but they did not do it. And then you adjust these coefficients for every word. And in reality, then you say that these coefficients is a representation of the word itself. Okay, so it's like if we have an image, let's say, and we say that there is this pixel number n, and then we adjust the weight from pixel number n to predict different classes of, you know, digits, for example. And then we say that probably pixel number n can be represented as this vector of the coefficients for each individual class. So instead of using the ID, we can use the vector representation for something.
So what's the advantage of that?
So compared to represented by ID itself, it allows to generalize. And also, like, computationally, it may be more efficient. Compared to getting these vectors by explicitly factorizing the matrix of occurrences, there is still ongoing discussion, mostly, you know, religious character. People believe one is superior, some others believe the other one is superior. But the novelty of work-to-vec and that paper was that they introduced some additional hyperparameters which you could tweak, like this maximum probability with which you draw a given word, or they like tried different sizes of the context, or they tried saying that, okay, we reverse this problem, and now we try predicting the context from the word itself. So there was some novel stuff, but in reality it all boils down to this factorization of PMI metrics.
So can you also give some example or some sense of what that vector looks like? I mean, what are those dimensions and so the K1s, the Ks are the coefficients
Yes.
that we're trying to estimate.
Yes. So oftentimes it is like normalized, it lies on some hypersphere, but this does not really matter. And the thing with distributed representation is that we cannot point our finger to any of them and say this is responsible for, you know, this. Like if we have movies, there is no single dimension which is responsible for the amount of cruelty in the movie or whatever. Though we can replace it, like we can insert some prototypical movies. But usually it varies, like the number of coefficients, the size of the vectors varies from dozens to thousands. Maybe it also depends on the size of your corpus, because the more like parameters, essentially these are parameters of the model, right? The more parameters you have, the more prone to overfitting you are. But in general, like for complex problems, it is the order of 1,000 or something. For simple stuff, you could even use, well, what is the smallest size of the parameters? It was only 3-dimensional as far as I remember. But again, the beauty of them is that they seem to capture some of the, you know, semantics of the words and relations between them, though this is nothing more than, you know, approximating some statistical properties. of words. And there is a common misconception that word2vec is like deep learning. It is not deep learning. It was actually the answer kind of by Mikolov to a paper published 2 years before. It was called NLP almost from the scratch, something like that. And there they learned these word representations, but as coefficients at one of the layers of a neural network. And they seemed not to capture all these nice properties as elegantly, probably because like the space was not linear. It was like there are still all these relations captured, but we warp the space by adding these layers in the neural network. Yes?
Are the coefficients created from the words? The coefficients are numbers, right?
Yes. So we start with small random values. I'm not sure if this is totally like okay to start with zeros, but it's better to initialize with a small truncated normal distribution around 0. And then, yeah, like as we discussed with stochastic gradient descent, they are pushed a little bit towards finding the better solution, towards minimizing the loss. And in this case, the loss is either with this negative sampling we drive the correct ID, like predicted to 1 and incorrect to 0, or it can be the same softmax as we discussed in the class classification. But this is kind of the magical thing of it, is that the model is not complex. It's just, if we talked about logistic regression and stuff, it is the model of that order of complexity. And still it gives things that look amazing when visualized. Yes?
So, for example, in this sentence, there's a word soup. So if the soup word occurs in another sentence, that's I'm in a soup, so it means a different thing. So there'll be two vectors representing the same word?
So there were approaches to represent polysemy by initializing for one word a few possible vectors to represent and finding the nearest. And maybe it works in theory, but in practice there is this problem with this ifs, right? If your code needs to run fast on a GPU, then it's better to have a bit more like simplistic model that is trained faster and you can afford training on more data, than to have something like more elegant. Perhaps if you make named entity recognition and then you make an embedding for entity and then you retrain it, then you would achieve some better results. But in general, if this would be an ideal like representation for bank as a river, and this would be ideal representation for bank as financial institution, then somewhere here you will have the stuff that you will, after all, learn. And also this balance depends upon how many examples of each kind you give. Okay, so talking about visualizing embeddings, there is this also part of TensorFlow, I guess it's now, it's called embeddings projector, and there are predefined data sets, and you can play with visualizing them. There are two widespread things, like algorithms to go from many, at least for the visualization purposes, from many dimensions to 2 or 3. This is PCA, which has been there forever. It detects the principal components, kind of the major vectors that go through the data, and it tries to come out with a system of coordinates that is rotated the way that it is aligned with this, major vectors. And there is this t-SNE, and t-SNE is interesting because it gives a really nice representation of local structure. If you want, to visualize clusters of data, and you go from 1,000 dimensions to 2, then t-SNE is the way to go. But with t-SNE you will not get illustrations like this. Most of these are created with PCA because t-SNE distorts the global structure. If man is far away from king and woman is far away from queen, then these vectors will look totally different from visualizing this. But again, I would encourage, you to go to this projector.tensorflow.org and play with these sets of data and with the ways they are visualized. You can click on any of the dots, or you can hover over them and see what it is. Okay, but now we have a representation for one word, and from it, how do we go to representing a piece of text? And this is a table which is, I'm not sure if it still holds true for me or not, but I prepared this about half a year ago for one of my clients to illustrate advantages and disadvantages. So in back of word, so averaging or do anything, any aggregation of word embeddings, we lose the sequence of items in the text. And then there are paragraph vectors which are kind of claimed to preserve it to some extent, but it's a bit simplistic because we assume that there is some linear way of how items are aligned. And then we can model a piece of text as the state or output of some convolutional neural network or as a recurrent neural network, and we'll talk about them in a bit more detail. So what is the motivation behind all this deep learning stuff? The models for both regression and classification that we've discussed so far assume that either the data is aligned close to some lines or hyperplanes, or that there are lines or hyperplanes that divide classes. So with really, really simple data, this holds true. With text, and if you're using really multidimensional embeddings, this often holds more true than it should have. Like you can build large linear models for text on like hundreds of thousands of dimensions, and it will give pretty good results. But it's not always true, especially if we go to the level of characters, not words. Yeah, there is one more thing which I wanted to discuss. It's composite representation, but I think we'll leave it for later. So the world is not linear, obviously. And this is especially true for images, for example. And for image engineering, they tried for a long, long time to come up with handcrafted features, to describe images. And these are examples of some simple kernels. Kernels is kind of, you can imagine it as sliding window running over stuff, and we multiply things together and get the result which depends on how similar what we have in the kernel is to what we have in the part of the image. And this is line detection, and up to 2012, I think, in these image classification competitions, there were, like, not this, but much more complex systems. And started with 2012 architectures based on deep learning started winning. And so this is totally old. These are like random images, but this illustrates the concept. So this is AlexNet from 2012, or something similar to it, maybe a part of it. So we are not talking about convolutions for now, we are only talking about the layers. There are layers in the neural network, and each of the layers is learning some representation of its own. And in the end, we have classifier, like we could have softmax here or something like that. But the classifier is still linear. But for this linear classifier, we come up with kind of space that is linearly dividable. And all this machinery is to come up with such a space. So I will not go too deeply into how neural networks work, but what is important is that we have a number of layers. And this is actually this is just the data. And the output is, similar to the regression or classification we talked about. What is interesting is that we are adding these hidden layers, and hidden layers transform the space in some way. But the problem is, if all these units were linear, so treat one of these units as linear regression, for example. a1x1 plus a2x2 plus etc. etc. So the problem is that if they're all linear, we still come up with a linear function as a result of combining all this stuff. And so after each of these linear nodes, we also add the so-called activation function. So this is the sigmoid which we've seen already. Also historically they often used hyperbolic tangent, which superficially is like sigmoid, but it goes from -1 to +1, not from 0 to 1, superficially. And nowadays they're mostly using ReLU. It's rectified linear units, it's maximal from 0 and x. So we have 0 up to 0. And the motivation, one of the motivations for the earlier approaches was the squashing of the inputs. It means that if I have 100 or some really high, really low value, I still bring it to some reasonable range. But then it turned out that it's not that important to have it, especially if you can renormalize afterwards. But the only thing that is important is to have some nonlinear function that is differentiable on most of the possible input values and you're good to go. So these ReLUs have their own problems, of course, so they tend to die. If we go like below 0, then the derivative is 0 and we cannot minimize the loss. So there were and there are attempts to make leaky rectified linear units is when we don't have this exactly 0, but we have slightly less of like slope, and this slope can be adjustable as well, but this works in practice. And again, like a copy-paste from some of the TensorFlow examples, if you think that it's all too complex, it's just one line of code in reality. And here we define activation function and the input and the number of output nodes. Okay, and again, I would encourage you to go to this deep playground and try building the models that predict some simple stuff. And what we can see among the other things from here is that neural networks have this possibility of approximating something that is not linear, but if you have a close look here, you will see these linear segments everywhere, which is an indicator that ReLU was used as activation function. Okay, so this was a really short introduction to neural networks. There is also this huge topic of backpropagation, and I wanted to share with you some visual illustration of it, but they told me the day before yesterday that it's not ready for publishing yet. I promise as soon as it is public, I will send you the links to it. So far, there is a really nice course on Coursera by Jeffrey Hinton, who is one of the founding fathers of deep learning. And also I added 2 blog posts describing the intuition behind how neural networks transform the space. Okay, and I think this is all for this part. We ended up yeah.
So you can actually get started with convolution a little bit, and then then we'll take into the next.
Okay,
I think we'll need some more time, so.
When you get to kind of digest CNN and then get back to it.
Yeah,
Yeah.
that would be, yeah.
Okay, so CNNs are easy. If you have image recognition problem, and then you say that each pixel is an input to some neural network and it does something with it, then it does not really go well with this location invariance thing, that if our task is to find whether there is a cat or a dog on the picture, then it does not matter if a cat is in the top left corner or in the bottom right. Of course, this could be fixed by feeding lots of images that are altered in some way. But also probably they did get some inspiration from these kernels that were hand designed. So they thought, why not make kernels learn themselves? And that's what they did with convolutional networks. So the convolution, kind of, it's mathematically probably it's not really convolution, but it's going with this sliding window and multiplying it element-wise and then adding up the sum, which tells you again how similar the path of the image to what is in the filter of kernel, it is called. And everything that they needed to do was again to implement this gradient descent. So you go with the convolutional, with this filter across all the image, and then you calculate the loss and you reuse the coefficients and you adjust them accordingly. But convolution is not the only thing used in convolutional neural networks. The other common operation is pooling. And they use either average pooling or max pooling probably more often. And this is just taking some window and finding the maximum from it. And saying that, in this case, 6 represents all this window. And the intuition behind it would be if the purpose of the convolution is to find some characteristic patterns, then the result from the window is just the strongest characteristic pattern. Again, if we're talking about these kernels, we don't train only one. We train a few to detect different kinds of patterns. Like with the line detection a few slides before, we could take 4 in hope that it will detect horizontal, vertical, and diagonal patterns. But it's more complex than this. And then in image recognition, they stack this convolution pooling to detect more and more abstract patterns. In language processing, for quite some time they did not, especially if doing simple tasks like sentiment analysis on word level, right? One of the items from the input is word as opposed to a character. And this is an example of it. So you represent every word as a vector again. You can either start from pre-trained embeddings, from things like word to vec, or you can train them from scratch. You can initialize them with small variables, and it will be indistinguishable from one more layer in the network, though in reality it's implemented as dictionary usually for performance reasons. And then you perform the same convolution operation. You come up with a stack of the patterns that you want to train, and you go with these windows along the text, and you adjust the parameters a little bit. And there is a pooling layer as well. And this is usually pooling over time in goes across this axis. What lacks here is if we want to stack this after pooling or after convolution, we would want to add some nonlinearity like travel. And then there are usually 2 in the simplest case. I never encountered 1 in reality. 2 layers of fully connected neural network. And then we have prediction. So this stuff with one convolution and one pooling is already enough to detect positive and negative sentiment in the text.
So Sasha, I think maybe you can spend a little bit more time telling us about convolution. Why is it called convolution?
So this is
maybe a simpler example. And I think it may also help to then, because I think this is an important one to run through again, this particular example.
Sure. So we have some image. So for the text it's less illustrated in a way. And we have a diagonal line in the image. And we maybe have all the empty things as zeros. And we maybe have a 1 here. And then we have this kernel, let's say it's 2 by 2. that we design manually, let's say. And it is this, and it is for detecting diagonal lines. And we go through this, with this kernel, through the image starting with this. In reality, not always, because we sometimes do zero padding. And we see how this pattern matches with the part of the image. And we determine how similar it is by multiplying the elements in a pairwise way, and then adding them up. So this will be 2, and if we have range from 0 to 1, this will be the maximum value for this kernel. Right, so we say that here it is 2. And then we take the next part of the image, we match it with the kernel, it will be 0, and here will be 0, 0, 1, etc. And afterwards, we will have, if we don't do zero padding, we'll have this 1, 1, 1, meaning that here we have elements of the diagonal line. Oh no, this will be 2 to 2, and here will be 1. And then we do max pooling, and with max pooling, we say that from this 2 by 2 part, I take the maximum value. This will be 2 and 0. And if we, for pooling, extend this image and 1 and 2. And then we can do the same, but with different kernel. And the key here, so this is called convolution. Then we do backpropagation to adjust the coefficients, and I'm not sure how to illustrate it here.
So what do we learn from that? So the last one, after max pooling.
So this is the representation, and we see that some pattern, the force is strong in here. Some pattern is strong here in these parts of the image. And then we do the same until we can actually roll it out to a vector here, and then use this as inputs for some classifier or something. And the classifier will know that if it had a class large diagonal line across all the image, then it would say, it looks like this and this are strong predictors for this class. And okay, let's reinforce this pattern. And let's make it not 1, but maybe 1 and 0.1 or something. And let's make this one negative maybe. I'm oversimplifying here, but still. And the next time it will come with stronger thing. But let's say that we tried to predict a cat, and it just so happened that we were unlucky to say it's cat for sure. And then in the next image we could have 4 ones in the square at the center as the cat, and we would say, oh no, let's back up a little bit. And probably the things that we learn, we're not that sure in them. And let's adjust it now to maybe 0, 9, and here plus 0, 1, because we don't really know what it should do. And in this way we adjust these coefficients a little bit until we find suitable patterns to detect the cat. Maybe this could be a part of large image, could be a part of the pointed ear of the cat or something like that.
So the outcome is essentially it's a 2-class problem, right? In this case, you're just saying if it's present or not.
So yeah, in this case, yes, but what it gives us is that this filter is common for all the image. And so if we have large image, it does not matter for it if this diagonal line is here or if it's here, it will still be able to detect it. And it is pretty much the same in text. We could view it as sliding window going along the text. It's both positive and negative thing that it does not matter, at least with one layer of convolution, if the words video and do are here or here. It will detect the same. And partially, that is why it works pretty well for sentiment analysis, because sentiment analysis could be done even with, I don't know, keywords or, backup words, something like that. So you map from the word to the positive or negative sentiment. Only that we take not one word but a few. And of course, we could do it with n-grams, but then the task would be either to make a separate parameter for each possible n-gram, which is for non-trivial like vocabulary sizes, it becomes hard. Or we could try learning like salient terms, kind of it was called in Google at least, to find these n-grams that behave differently from just the set of words. Kind of they have different context or something. And this is a pretty hard task in itself, while this tries to do it automatically. And if you have it, like the more layers you have in convolutional networks, the larger the effective window is at the start, and you can start detecting dependencies between words that are like 3 words apart, 5 words apart, etc. There is a separate, very interesting topic of how convolutional neural networks were used for like acoustic modeling by DeepMind, but I think this is far beyond the scope of this one. But anyway, yeah, it all boils down to detecting characteristic patterns in the text.
So can you say something about the kernel for in this example?
So numerically it would be hard to imagine something, but let's say that it's total oversimplification, but let's say that one here in the first position means a verb, right? And one in this position means a noun. And there are characteristic sequences of nouns and verbs, and it will sooner or later, if it backpropagates here to this layer, it will learn in the kernel that, oh, this is a pattern of a verb following a noun. And this is a pattern of a verb following a noun, but with something in between. And then maybe it will capture something about this missing part. And if we do more than like 2 by 2, there could be, like there is word 1 that is meaningful, that there is anything between them, and there is word 2 is meaningful. It can learn even like patterns like this, that we're not sure what is here, but it does not really matter as soon as these 2 words are present. And again, with pooling, if we go up and up, what we are losing afterwards is the ordering of words within this window. And there are some of the approaches that feed this information additionally. There are some people who, like, in principle, do not use pooling because they think it loses some part of information.
When you say design the kernel, it's really just setting some sort of things for it to look for.
So here the networks learn it by itself as opposed to like handcrafted features, but still we express our beliefs when designing the system because we set the size for this window context, and we also like determine things like stride. Stride is how many points we jump. So here in this example for pooling, the stride is 2, right? So we jump from this to this. We could say that, oh, there is something valuable here on the boundaries, and we can set stride to 1, but this is kind of losing the essence of the pooling, which is to compress. You know, here we have 4 by 4, here we have 2 by 2, but we can manipulate all these things. And do I have a piece of the? Oh yeah. So here is an example from TensorFlow. There is also padding. Padding is whether we are adding zeros around. And we could choose to add them not to lose this information in the corners, or we could use to skip it to compress our parameters of the possible solutions a little bit. So here is an example of declaring the convolutional network, and then convolutional layer, and then ReLU. In TensorFlow, So again, it is only to illustrate that it's a few lines of code. And here is a function for max pool. Yeah, and also, yeah, here we define the size for the pooling window, for the stride, and also the same for convolution. And this could be, like, we are not obliged to only use window of one certain size. We could say that if we are analyzing text, then maybe there are some useful patterns of size 2, and there are some useful patterns of size 5, let's say. But again, these are our assumptions which we use when designing the system. And the only way to go around this, these assumptions is to use fully connected network, but then again, in the number of layers and the number of units and the way we initialize things, we anyway express something that we believe will not work. Okay, so maybe while Chirag is looking for lunch, we'll have one more thing. It's not necessary that we use only one column of layers. Here we have one of the things that I did for Brainly. We had similarity between questions. And we have question 1 and question 2, which are fed to the convolutional networks. Everything that goes up from here is some kind of vector representation. And so they are concatenated and they are fed to the feed-forward neural network, which tries to predict the similarity score. And similarity score is kind of some function of probability that these two questions were answered by the same user. And for it, I use negative sampling because the questions don't have IDs. Well, they do, but for generalization, it is like not a good representation. And therefore, what you could do is either to try to predict a vector and find some question by it, or use negative sampling, so make score higher for questions that really belong to the same user, or make score lower for questions that are just drawn randomly. And again, these networks don't have to be the same. If we have a problem of telling whether the answer is good or bad, I'm not talking here about the semantics, etc., the correctness of the answer, but just the format. We have question at one side and answer on the other side. We train one convolutional neural network for question and the other for the answer, and even the representations of words are different there. And then again, we put a few fully connected layers, and we predict the probability that the given answer was removed by the moderator. So these are like a bit more complex things. One more thing that often occurs is, let's say we pre-trained embeddings on some task on Wikipedia, okay? But we have a problem of sentiment analysis or something like that, so we cannot really reuse these embeddings. One of the possible solutions would be to backpropagate into embeddings layer and change this word representation a little bit according to our task. And the common problem with that is, it is called catastrophic forgetting, that while the top layers are still learning, they're destroying the information in the bottom layer. And there are lots of different techniques, less and more complex. One of them is to freeze this representation for the first few iterations of learning, while these upper layers are trying to figure out something for themselves, and then at some point we enable backpropagation to the first layer to differentiate between awesome dinner and awful dinner. But there is also another solution. We freeze the... So here is a part of the network is our pre-trained embeddings, and let's say above it is a CNN or anything. And we freeze those, and then there is some classified maybe there are three connected layers. about them. Then we say, okay, this part is not able to tell awesome dinner from awful dinner. But what we add to it is some box that is like word embedding, so it could be anything. That is able. And this is frozen, this is straight, and this is straight. And oftentimes, this is a model of another level. This is a character level model. Okay? And this may be some CNN 2, this is CNN 1. This is a network trained on the character representation, and we don't pre-train them. And we use both as inputs to the fully connected layers. So we don't have this problem of catastrophic forgetting or the problem of choosing some thresholds or adjusting learning rates. Instead, we say that this part captures lots of prior knowledge from Wikipedia, and everything else is trying to compensate the difference between Wikipedia and whatever kind of text we are working on. And this is similar to, like, if we have a problem of movie recommendations, and we could, of course, use the collaborative filtering and build embeddings for movies and find the distances. But what if a new movie is released? How do we tell if it's good or bad for a given user? And then we go, where is slide 5? Here. We say that a movie is everything, the sum of embeddings of everything we know about it, or some subset, plus maybe some unique component that is not captured by everything else. So Deadpool is action and comedy and superhero movies, and we take the centroid of all these vectors, maybe weighted even, plus some buckets that we define, plus anything else, but plus some unique component, because one action comedy is different from another one in a unique way, possibly. And the same we can do with users. We represent users as a sum of the centroid of the items in user profile, maybe with some time decay for all the things, in order for us not to, learn that for this user ID, this and this movies are good. And even if you have the stable space of like products to recommend or anything, the users are constantly changing. The real system for recommendations is acting immediately after the user acts. If I start clicking on things like in Amazon, the ideal Amazon will change my representation on the fly without the training.
All right, so I think we can, and the food is also here. All right, so this is the end of the second part, and you want to say something about the third part?
So
after lunch?
for the third part, I have only RNNs left, and this is like 20 minutes. And then we can do Q&A or have some more pizza.
Yeah. Yeah, then that'll be great. Okay, thank you. So